Okay, I'd like to welcome you to my talk, openwrt hacking. And first of all, I'd like to start off with this year. Previously on What the Hack, I did another lecture on openwrt that focused mainly on the user perspective of the system, like how you use it, how you can configure it, install your software, etc. And this time I'd like to present the developer's perspective, because I think it's actually more important than user perspective in this case, because openwrt mainly started off as a development platform for creating custom firmware for the routers. And first of all, let's have a look at what I'm going to talk about today. First, the obligatory what is openwrt. And some short notes on what's new, what has happened in the development process of openwrt. And then I'll continue with the main part of my lecture, namely building packages and images with the developer tools that we provide. There are certain tools, the software development kit and the image builder, that we provide to make it easier to create packages and images from scratch while maintaining compatibility with the official releases. And later I'll go on explaining in depth how you can actually port packages to openwrt and what the syntax of these makefiles looks like and so on. And if there's enough time left on the third point, I'm going to talk about the structure of the build root, which is our source code base. Let's start with what openwrt is. It is a Linux distribution for embedded wireless routers, and it is designed to run on inexpensive hardware. So it can live with the space and RAM constraints of the average wireless router that you can buy on the market today. And of course, it is free software under the terms of the GNU General Public License. And let's talk about the features of the stable version. It is based on Linux 2.4, mainly because of the wireless driver that we got from Broadcom. And it only supports a single platform. The standard Broadcom platform, perhaps the most famous of it, is the WRT54G from Linksys. And the development version, which we're currently working on, changes the single platform thing. We made it cross-platform and added support for a lot of other machines. It also includes the new Linux 2.6 kernel for some target platforms. The first additional platform that we added was Texas Instruments AR7, which is used in DSL routers like the WAG54G from Linksys, the wireless ADSL gateway. And we also added support for embedded x86 PC-compatible hardware like Circus or Wrap. And another planned thing is the Atheros system on a chip, which is used in some of the more expensive access points with using Atheros wireless cards. And another thing that we've planned is support for the Microtik router board, which are also commonly used in some larger wireless setups. So what's new in openwrt development? Our version 1.0, codenamed White Russian, of course has lots of bug fixes over time. It's not quite there yet, and maybe in a few weeks we'll release another release candidate of it. But the main new thing that has happened in the last weeks or month is we finally got a web interface. I guess the pressure was just too hard. Users were requesting it. It doesn't really make sense to us as users, but quite a lot of people need it. And we currently have 122 source packages in our repository. So it's quite a lot of software, but the new version is going to offer even more. And we also added new scripts for handling system events. So with the current code, you can actually, if you have a router that supports USB, just plug in a hard drive and it will get automatically mounted. And you can also install custom handlers for system events like that. And we also improved the performance of the system quite a lot. We took off several seconds of boot time, mainly due to some changes in BusyBox. Okay, the development version of openwrt adds some more things in addition to that. First of all, the new platform support, which I already mentioned earlier, and of course also the new kernel. We currently at 2.6.15 and release candidate 6. And in the development version, there are actually 239 source packages, so a whole new lot of software got added. And you can have a look at our snapshot builds to figure out what these packages are. There are just too many to name them here. Another thing in the development version is that the network scripts got rewritten to support more dynamic configuration. A lot of people are using the wireless distribution system, which creates point-to-point links between access points, and with the new network scripts, you can actually generate real configuration for these kinds of devices without using some nasty script tags for that. And another thing that we added is new drivers for the switch configuration. Previously, it was very switch dependent to do some custom VLAN configuration, and there were some tools, but all of these are now considered obsolete because they break once in a while with a new kernel or different Ethernet drivers. So we got around to writing a simple configuration API for the kernel with drivers for the two commonly used switches in the Broadcom platform. This will also be extended to the new platforms like AR7. And another, I think, major happening is that we have a working Linux 2.6 port for the Broadcom platform. And we're currently working on integrating the free wireless driver. So the Broadcom platform, which previously depended on a binary-only wireless driver, will soon become a truly free platform. Okay, now to the main part of my presentation, the developing process. Our build system, which we refer to as build root, is based on the uclibc build root. Now, if I just say build root, you can assume that I'm talking about the openwrt build root, which deviated a lot from the uclibc code base, which we inherited. And it is mainly written in GNU Make. It doesn't use any special things for the standard building stuff. But we also have some shell and Perl scripts here and there to make things easier. And we also use a configuration system which is based on the kernel config of Linux 2.6, which you're probably already familiar with if you're using Linux. And the main feature of this build system is that it automatically builds toolchain packages and firmware. So you don't need to worry about downloading the single components which make up a whole Linux system. Just grab a source code and it will do all these things automatically for you. Now to the developer tools that we provide for special cases. The first one is the software development kit. It is generated from the build root at build time if you select it in the menu configuration. And its main purpose is to just compile packages without all the hassle around. It contains a precompiled toolchain and all libraries, and it uses build root compatible package directories. So if we have a standard format for cross-compiled packages, which consists only of build instructions. And the software development kit is actually a stripped-down version of the build system, which just builds the packages and creates some binaries which you can use. Mainly, it's important to preserve or to maintain a package across several versions of openwrt. especially important with our development part, because some library changes make it impossible to run newer packages on the older White Russian system. So you can just use the software development kit to backport these packages. Some short notes about using the software development kit. The first step is to just pick your package directory with the build instructions, copy it into the package directory of the software development kit. If you add several packages, which you can do, and these packages have dependencies on one another, there's a makefile which contains some examples on how to add dependencies. And you can just note these dependencies there, and the build system will take care of building the packages in the right order. And the last step, of course, is just running make, which will generate the packages for you. Now, the second tool that I'm going to talk about is the image builder. The image builder is also generated from the build root, but serves an entirely different purpose. It builds packages from image lists. So if you're using openwrt and you're basing your things off the official releases, and you just want to add some custom configuration files or some packages, then you can just use the image builder, add your special stuff to it, and have it generate a fully working White Russian based or Kamikaze, which is the development tree based image for containing all your changes. In order to build these images, it contains all the packages, the kernel, and the required tools for building the actual firmware images. So only the necessary stuff. Again, some short notes about using the image builder. You can add your custom packages to the packages directory. You will find all the standard packages in this directory, so just put it in there. And if you want to add some extra files, there's also an extra folder for that. This image builder actually uses several package lists which describe what the image should be made of. For example, we have 3 different standard configuration for the White Russian images. We have, of course, the default image with the standard set of features. Then we have a micro image which contains less packages and will in the future be able to run on devices with only 2 MB of flash. And then the third one is a PPTP package with the standard feature set except for PPP over Ethernet support removed and added support for PPTP, which some brain-dead ISPs still use. And as usual here, the last step is to just run make and it will build your images. Now I'm going to introduce the format of a package directory which describes all these build instructions. The first file, the config.in file, is the menu config description. You can actually leave that out if you're just using the software development kit to compile your package. This is mainly useful for integration into the full build root source. And then there's the main make file containing all those instructions. Was there a question back there? No? Okay. Then you have a folder containing all the IPKG control files and scripts. As you probably know, IPKG is our packaging system, which is similar to DPKG from Debian. And it also uses control files with much of the same structure that describe the package name, version, architecture, and stuff like that. Because you can build several binary packages from one source package, we actually have a folder there where you can put all these control files. Okay, then there's another directory called patches. If you're cross-compiling software, you will find that most of the time you actually need to change stuff in order for it to work. Most of the time it's the configure script. Autoconf is that way. You can just put your patches to the source package in this patches directory and make sure that that your patches are to be applied in the alphabetical order. And the build system will actually, when it downloads your files, extract them and patch them automatically, so you don't have to worry about that in the build instructions. And then there's another directory which is used kind of freeform, but usually called the same just for sake of having a convention. In this directory, you can add extra files which are either important to the package itself or to the build process of the package. Sometimes you need to pre-generate a config file, and this is the place to put it. Now let's continue with the first file in a more in-depth look. The syntax is, as I already mentioned, the Linux 2.6 kernel configuration format. And this is an example of what it looks like for a standard package. The first line defines the config entry. By convention, all configuration names for packages start with BR2, which refers to the build root 2 of the userlibc build root that we got some of our code from. And the second line, the select, is actually our way of handling dependencies. If one package depends on another, rather than adding a depend line on it, we add a select line, so that if you select this package and it requires another package, it will automatically get selected by the menu config system, so you don't have to look around for all the missing libraries before you can select the software that you want. And this is defined as tri-state. This tri-state thing probably needs some more explanation. We have three states for a package selection. First, you can deselect it completely. It will not get downloaded or get built by the build system. And the second state is selected completely. If you just select yes on the package, then it will download the package, compile it, and embed it into the resulting firmware image if you're using the build root. And then there's the third state, which probably caused most of the confusion, if you select it as module. Now, if you look at the kernel configuration system, if you select the package as module there, then this usually means that you have a separate object file after the build, which you can load into the running kernel. Now, openwrt packages are much in the same way. If you select the package as module, then it will get downloaded and get built, but it will just not get embedded into the resulting firmware image. So you have an external package which you can install into the firmware on the writable file system at any later time. Another thing, this also applies to kernel modules. So if you select a kernel module, it will not get built into the actual kernel that you have. It will just get built as a package and embedded into the firmware image. Okay, after that, there's the default which you can set. It's usually either yes, or we also use default M with an if constraint for the developer selection. To know how this works, you can just look at other packages. We have lots of examples in our source tree. And the last one, of course, is the help text. Now I'll show you what this looks like. If you open the menu config, you see here the highlighted item is the configuration that I added previously with the name after the tri-state command. And if you go on the help text, you will see something like this, with the name of the actual config option and the help text. Now to the actual package makefile. This is probably the most difficult thing for new package porters to understand. We have a standard format for makefiles because we use a lot of common code, most of which is already included in the first line. You see, it includes the file rules.mk from the top tier, and the responsibility of this file is to set most of the variables that are important for cross-compiling. It makes sure that that all the directories that you need access to, like the staging directory where the toolchain lives, or the directory where the binary packages go, that these are all accessible. And after that, you see a lot of variable assignments. You should always use these names because some of them are only used implicitly. So always stick to the template. The first one, obviously, is the package name, and the second one, the upstream source version. As you will see in the later PKG source variable, these are usually used in your other variable assignments as well, so you don't need to duplicate everything, and it's easier to change the templates. The next one after version is the release. This is usually openwrt specific. Over time, you will, most of the time, make changes to your packages, and this release indicates your version of the same upstream release. And the next variable is also quite important. If you instruct the build system to download packages from an external source, we use MD5 sums to verify that the download is saved correctly. So if the getter program for some reason cancels during the download, then this MD5 sum will obviously not match, and you will see a more descriptive error message instead of just a tar error or something like that. And in the next variable, in the PKG source URL, you will see some special syntax that we added for source URLs. Because SourceForge uses a lot of dynamic mirrors, we have added this special syntax to download packages from SourceForge. It will automatically fetch the package from a random SourceForge mirror. But in this variable, you can also add regular URLs. It doesn't matter. The next variable is also quite important. It's used both for downloading the actual source, because you see the source URL is not the full URL to the package itself. It's just the URL to the actual file that gets downloaded without the file name part itself. And the file name part itself needs to be added in the line below. This has the following reason. If you download such a package, it will usually retain its file name, and the build system needs to know about that so it can extract the file. And another important variable below that is the PKG cat variable. Sometimes you have bzip2 compressed archives, and sometimes you have gzip compressed archives. And again, the build system needs to know about the difference between them. So you can specify the command which will extract the compressed part of the tar file and pipe it to tar itself. And the last of these pre-assigned variables is the build directory. If you download a tar file from an upstream source, you usually get a directory, an extra directory, if you're extracting the package. And again, the build system needs to know about that, so you can specify this directory in this PKG build-dir variable. And the last line is for activating all the pre-formatted, pre-compiled targets which we have to make the build process easier. I will go more into detail in the next slide. This was quite a lot of information, I think. Are there any questions so far? No? Okay, then I'll just go on. The first important part of the actual binary building part of the makefile is the package declaration, which uses a template that we wrote. You see, it calls the template called PKG template, and the first parameter is actually the name of the config without the standard part. It is also used in several other instances, which you will see later. It's mostly the base so that you can refer to a specific binary package that you're building if you're downloading, if you're building several packages from one source. So you need to differentiate between them. The next one is actually the name of the binary package as seen by IPKG. This is also the name of the control file, and usually for most cases it's enough to just write the name in uppercase once and in lowercase for the other parameter, and it would just work then. And the next parameter after the backslash, which isn't actually present in the original make files, it's just to denote a line break here. Now, the next parameter is the package version as seen by the IPKG package. If you look at the slide before, we differentiate between the upstream package version and the package release, and in the actual package version that we have here, we combine both into one. And of course, the last important parameter is the architecture of the package. Mostly, this is set at build time already, but sometimes you may want to have packages that work on all architectures. And so you can just fill in all here instead of the arch variable, which, by the way, is preset by the build system. Now, let's look at the important build targets. Usually, the process for building a package is first you extract the package. The build system already completely does that for you without adding any extra makefile targets. And the next step is to run a configure script, which may or may not be present in the package. So the first actual package building target in this makefile is the .configure target prefixed by the package build here. So where the comment is run the package configure script, there you can actually put the custom commands that you require for cross-compiling, for running the cross-compiling configure script. And the last line, the touch, is only to let make know about the successful run of the configure target. So it will handle the dependencies correctly. If you're familiar with the makefile syntax, you will know this from other packages as well. This is just simple stamp files. And another target, a typo here, it should just say build. This works actually in the same way. You just add the commands here to run the main make process of your package, because usually you start off with a configure, then you run a make, and then you can, if you use multiple binary packages from the same source, split the files off in several packages. And now the important package targets which apply to binary packages. You see here the variable IPKG strace is actually preset by the build system, and the uppercase strace here is actually what you specified in the line. Let me go back. Oh, here it is. This uppercase strace here, this is the same name that you also use in this variable. And what this package should do is copy all files into the directory which is given by the name idr strace in another variable, which is also again set by the build system. The final command for this package build is usually the same for all packages, except for the name part. You usually don't need to change anything in that. It will run the IPKG script for building the package. Okay. Now some extra targets. Some packages may need to behave differently if you clean them, because sometimes you have a large package which takes a lot of time to uncompress and to patch, or maybe sometimes you want to make changes to the actual extracted build directory. So you can add a target that we refer to as mostly clean, which basically just runs make clean in your source package directory. If you don't add this target, it doesn't matter, then it will just detect that the mostly clean target was not run. By the way, the mostly clean target should also remove the stamp file for the package build. Because if the build system doesn't detect that the stamp file for the build has been removed, then it will just assume that the mostly clean target failed, and it will run, it will clean the whole directory and all changes that you may have made. So if you want to make some manual changes, add this target. Then there are some other extra targets because sometimes you not only want to have a binary package, but the package may also contain a library which contains development headers and extra files. And these may need to be accessed from other packages as well. So you want to copy them into the staging directory then, where, as I said, the tool chain lives. And there are some standard targets here, which are called compile targets and clean targets. And you can basically hook any extra makefile targets into these targets by adding a dependency. And compile targets will be run directly after the normal build process, and clean targets will be run directly after the make clean has been run, either by running mostly clean or by running the normal clean process. And what you usually do is on the extra target added to compile targets, which we mainly call install dev, you will just run the necessary make commands to install all development related files into the staging directory, usually by just running make install on the source directory. And the same goes for uninstall dev, except that for most source packages there is not a make uninstall target, so you should remove them manually by adding rm lines there. Now to the final part of this lecture, some short notes about the structure of the build root, because sometimes you not only wish to port packages, but also create a derivative version of our build system, or just integrate some packages that you may wish to submit to us so we can include them. And or if you just want to port it to another platform, you need to know some basics about the structure. There are several source directories which we use. The first one of which is toolchain. You usually don't need to change anything in there. It contains all the build instructions to fetch the kernel headers, the bin utils, the C library, and of course the compiler itself, and additionally also the debugger. Most of the time for porting a platform, this is not needed, except if it's a completely new architecture, then you may want to add a configuration for the C library there. The second source directory is package, which contains all our main packages, but not all of the packages, only the ones that do not depend on specific kernel tree features. So if you're building a kernel module, you usually put it in the next directory, which is called target. And this directory contains all the build instructions for both the firmware image generating process and the kernel building process itself. Another additional directory is the scripts directory, where you can put some extra scripts that you may need for several packages at once. You will find the Perl script in there that does the download, and some other IPKG related stuff. There are also some important directories for the actual build process, which are generated at runtime of the compile process. These usually correlate to some of the source directories. For example, the toolchain build directory the arch here is replaced by the architecture that you're compiling for. So on White Russian, the standard is toolchain build mibcell for MIB's little endian. This contains all the source directories for the toolchain related build. So it is only used at the initial generating of the toolchain, and later in the process you don't really need it anymore, but you should keep it for the build stem files. Probably the most important directory is the staging directory. This is where the build system collects the precompiled toolchain and all libraries. I've talked about this directory briefly before. This is also the main component of the software development kit. So if you don't need the build system at all and just want to compile some packages, you will find all that you need in there. The whole toolchain, the libraries, the development headers, all this stuff. And then the last important directory is the build directory. This is where the kernel is built, all the packages are built, basically everything that lives in package and target directories. Oh, I explained this already. Another thing, the target directory also generates the image builder, and the software development kit is generated by package. Now this is an excerpt of the actual output of the make process in our development tree if you don't enable the verbose options. It will actually show you in what part of the build process it's in. So if you run a make process, it first starts off by installing the toolchain, which calls some extra targets later. So the second line in here says toolchain kernel headers prepare. This means that it runs the prepare step of the kernel headers directory. This kernel headers directory doesn't actually have any other useful targets. And basically all what this does is it unpacks the kernel headers required for the compiler build. The next step is to prepare, compile, and install the bin utils. By convention, the standard things that these targets do is prepare, unpacks the source directory, then applies all patches, and makes sure that make knows about the status of the package. And the compile target builds all the binaries in there and also builds the packages if they are present, which they're obviously not in the toolchain. But another thing that it does, as I explained previously, if you want to install development files into the staging directory, this is also done in the compile step. And the last step, install, has a kind of a special meaning for the toolchain directory in that it doesn't really embed any packages into the firmware image, which it would do in any other directory. But in this case, it just installs the toolchain related part into the staging directory. So if you look at this part of the excerpt, the standard process is first unpack the kernel headers, then build the bin utils, then prepare the GCC. Actually, preparing the GCC in this case means that you build the so-called initial GCC. The initial GCC is, it can only create statically linked executables, and it is only intended for compiling the C library, which we'll use later. So it then generates the initial GCC, and after that starts compiling and installing the C library. And after that, when it has generated the C library, it will build the final compiler. This is actually a necessary step in the toolchain building process, because if you don't have binaries of the dynamic loader and linker ready, then the compiler cannot create, compiler cannot be created to target the actual C library. Now the second part of the build process involves preparing everything for compiling packages by compiling a Linux kernel. Many packages don't actually depend on specific versions of the kernel, but nonetheless require an already compiled kernel image because of some header issues. And this is what all this does. It first calls the prepare target in the target/Linux directory, which in turn compiles the actual kernel image. In this case, it is differentiated between Linux 2.4 and Linux 2.6 because at the moment we only keep one version of each in our build instructions. So if our Linux 2.6 kernel is set to the latest 2.6.15 kernel, then all boards that we have target this kernel, and all the build instructions for this version are in the target Linux 2.6 directory. Then the next step is to prepare all the tools that you need for creating the target image and actually compile the Linux kernel here. The order of these targets may be a bit confusing, but if you actually look at what these targets do, then it should be relatively clear. Okay, the next step is to run the compile target in the package directory, which will call all the compiled parts of the individual packages which you will see later. So it starts off by building the base files, busybox, and some other packages. So this will actually generate all the IPKG files which you can install later. And now to the final step of the build process, which also kind of concludes my lecture. It cleans the root directory, which it keeps, because the standard process is if it embeds all the packages into the firmware, the firmware image, it needs to build a copy of the root file system first in the directory. And if you have changed some of the configuration, then the package selection has also changed and you need to regenerate this copy of the root directory. So the first step before doing any actual package installation is to remove this temporary directory. And then it just installs all the packages that were selected by calling the install targets. And then the final step of this whole process is to install the Linux kernel and all its modules into the directory which keeps track of the root file system and the extra files that are needed to build the firmware image. And then you can also see a special directory called target Linux package, which I haven't mentioned before. This is where all the package directories for kernel-specific stuff live in. So if you're building a kernel module which is not included in the kernel tree, then you can add the build instructions to target Linux package, which works much in the same way as the original package directory. And the last step of the build process, of course, is to install everything and generate images, which is what target Linux image install does. And after that, the build is complete. We still have some time left for questions. Do you have any questions? Yes, over there. The microphone is over there.
Yeah, I'm a happy user of openwrt, so thank you. My question is, you probably know about open-embedded, and when I look at your software development kit, it looks very much the same as the open-embedded stuff, which is used for PDAs and which was used for the mesh node, mesh cube, and even for DVD recorders and such stuff, so for embedded Linux. Is there a reason why you did develop, some kind of reinvented the wheel, or?
Well, OpenWrt, when OpenWrt started off, it was, I think, kind of never considered to use the open embedded stuff. I don't know how ready it was back then, but basically we started off using the UClibc build root and kind of went on developing from that. And there was some discussion about whether we should use open embedded or not, but none of the developers really like the way in which it works, and so nobody really wanted to port OpenWrt to open embedded.
Okay,
So,
thank you.
Any other questions?
Hi. I'd like to know how difficult it would be to port it to the Cobalt Cube.
What architecture is it?
MIPS-L.
I don't think it's very hard. If there is an existing port for the Linux kernel, then it should be relatively trivial. So if you're porting to something where packages for the architecture already exist, basically all you need to do is take the OpenWrt kernel, which we have, with all the generic patches that we use, then add support to the target that you're using, and do a diff again, so you have one patch which only contains the platform support for your system, and works with all the generic patches that we have, and then you only need to copy that in and change maybe 2 or 3 lines in some makefiles, and you have another target.
Yes, it has other PCI bridges and other network hardware. It uses DEC tulip chips.
It uses what?
DEC tulip chips. DEC tulip.
I don't know about these chips. It's probably just a matter of adding the drivers and maybe making some small changes to the init scripts, which are kept pretty much generic for different hardware. Because you see, we already ported our stuff to some different architectures like AR7 or the embedded x86 stuff. So mostly it's just a matter of trying the image and seeing what doesn't work, which usually isn't much.
Because of it has a hard disk, so it would be easier to develop something for OpenWrt on that platform and then just compile it for a smaller one.
It probably would work that way.
Okay.
If you're interested, you may want to come over. I'm usually at the wireless community corner, and maybe we could see if we could get this platform integrated, if you're interested in working on this.
Thanks.
Any other questions? Okay, then thanks for listening.